that you're dealing with a metal. But the only complexity in both enter in through the complex index of refraction of a metal and the usual way of absorption, and so on. Now, what happens? Well, in the meantime, over in Germany, a young physicist trained under Hermann von Helmholtz discovers the existence of electric waves, which the British had doubts about. That is, they thought light was electromagnetic, but they didn't think it was going to be likely possible to generate this stuff artificially. Hertz, it's a long, complicated story, working through eventually from Helmholtz's work and then through Maxwell's equation, generated electric waves, and in 1889 wrote this extremely influential paper, including the first depiction of the field maps around a resonator. You've probably all seen pictures of this before. It gets reproduced to this day. They were drawn by hand by him and his wife. These are the equations he used to do so, something Cheng-Pang and I are working on now. And when you feed his equations into, say, MATLAB today, you get just that, exactly what you would expect. And he is the first to have done something like this. A brilliant piece of work. Let me add, interestingly enough, the one thing that you don't have in Hertz's work is you don't have a radiating emitter. You see there's a little circle around here over what looks like an oscillator. That circle is, inside that circle is no man's land. Why? Because he refuses, with good reason, to deal with the vector potential. His system of equations here are actually all source free. So it's all in free space afterwards. But yet he was still able to produce these things. So now we know that electric waves exist. Now, a lot of activity starts further in field theory because of this. Now we know that such things as light are electromagnetic in structure. And so further investigations begin, and they begin principally in the first place in Leiden in the laboratory of H.A. Lorentz. And Lorentz has a series of students there. One of them, not known very well today, is a fellow known as, whose name is Remelt Sissing. And he builds this very elaborate device here. There's a polarimeter in here. You could send light through it. There's a magnetic field here. And there's a mirror which the light reflects off of. You can control the direction of the surface of the metal in respect to the magnetic field. And then there's an analyzer over here so you can test the polarization that comes off. And this is designed to explore the Carr effect in detail, which people are now very interested in because of all these things. And two types of observations are performed. One type, the polarizing and analyzing prisms are set to minimize the light that comes out over here. And one in which you rotate them around so that you can turn the elliptically polarized light that comes, it was linearly polarized, becomes elliptically polarized, and then if you rotate this right, you can turn it back to linear polarization. And the nice thing about it is that the minimization experiments have high amplitude sensitivity, but the linearization experiments have high phase sensitivity. So with these two, you can explore amplitudes and phases quite separately from one another. And I remind you, this is a tiny effect. Now, Drude never calculated phases and amplitudes directly, as he certainly learned about these experiments. Because, why? Because he thought that the experiments that Sissing was producing agreed with less accurate ones that were produced in Italy by a man named Augusto Righi. He just calculated certain rotations. But even so, using Righi's, he found deviations from theory in the linearization rotations based on the equation that he and J.J. Thomson had independently developed. Now again, the phase factor here in this term over here is just due to the usual metallic reflection property of iron, its absorptive property. And what this works out to in the case of iron in these experiments is that it should come out to be about 76 degrees in 16 minutes. And these observations, by the way, require you to measure very carefully into small differences down into the minutes, sometimes fractions thereof. But Sissing's experiments seem to require that this factor here has to be about 84 degrees, 53 minutes, a considerable difference between what it should be on the basis of this here. And this was way too large for the accuracy of the experiments, but it was hard to tell. I have spared you the horror of seeing what Druda's calculations look like in these things. They don't have computers. They don't have calculators. They've got slide rules. Trying to see what the errors are in the phases and amplitudes for that matter by estimating the errors in setting the polarimeters and so on is close to impossible by hand. I ran it through years ago, but of course I used a computer. So there's room for argument at this point about these things, at least given the deviations that are being found right now. But, yeah. Now, Lorentz had another student by the name of Peter Zeeman. And Zeeman was very interested in this, and in fact, he expropriated Sissing's apparatus after a while. And he called the difference between the 76 and the 84 the Sissing phase. It's a problem, but not clear how much of a problem it is. At the same time, another German physicist who was actually the world's leading expert in metallic reflection by the name of Eugen Goldhammer insisted that if you really want to take account of what's going on, you should add an additional phase factor over here. Now, let me again emphasize, this H term here is supposed to be entirely real. It's a field. The only reason for any complexity here is because of the presence of conductivity from before. All the extensive parameters were all real. Complexity only comes out running through the differential equations using conductivity. So if you have to stick something like this in here, it's a puzzle as to what that could possibly mean. Got here. So here I've drawn a couple of graphs in which I'd calculated a long time ago on the basis of their equations and the experimental results what things look like. Now I put error bars on here because I ran things through the computer, knowing what the accuracy of the setting the polarimeter and so on were. And we can compare things for the two types of experiments, actually. This line, the dark black line here, is what corresponds to what this guy Goldhammer produced by introducing an adjustable extra phase constant, lambda. And you can see here that the Druda and J.J. Thomson equations without that parameter fall way out. So in fact, Sissing's discovery had, in fact, if you could have calculated this out, given these differences, shown that there was already a failure. But they didn't know that because they couldn't really calculate it through given these distances. What you needed was a bigger difference. See if you could generate a bigger difference. Now, how are you going to do that? That's what Zeeman started to do. And that's what set him on his career. Here's Peter Zeeman. Well, this difference over this constant had generated a pretty bitter controversy between Paul Druda and Goldhammer, because Goldhammer was actually claiming that Druda's competence in calculation was in question here. It was a rather nasty situation. And of course, because if you do have to stick this extra phase parameter in, then the entire deductive structure that Druda and J.J. Thomson, for that matter, had built collapses, because you're pushing yourself into a realm where you have no idea what can possibly be going on. And in fact, it called into the question, they thought it called into question the very possibility of working with purely extensive macroscopic parameters. Remember, no microphysics here. 1892, Zeeman, as I said, takes over Sissing's apparatus and replaces iron with cobalt. Cobalt is much more magneto-optically active than iron is, as it turns out. And what happened as a result? Using cobalt, knowing the values of the usual complex index of refraction for cobalt, which had been well measured by this time, you find huge differences. The Thomson-Drude structure should be 65 degrees for these phase measurements. In fact, Zeeman measures 49 degrees. That's huge. There could be no dispute that there is something wrong here, something fundamentally wrong. You've got to put that extra phase constant in there, but what can it mean? Letters went back and forth between Zeeman and Drude. Zeeman didn't really have any theoretical irons in the fire, so to speak, unlike Goldhammer, so Drude listened to him. And he became convinced, and he conceded that you had to stick this in somehow. What happened? He thought back to something that was being done just around this time by Hermann von Helmholtz, Hertz's teacher. Now, I don't have time to go into the way in which in 1870 Helmholtz had created an alternative structure for electromagnetic equations, which under certain limiting conditions was equivalent to field theory. That's a long story in itself. But what is significant for us is this. Helmholtz was very interested in the discovery of something called anomalous dispersion. So anomalous dispersion occurs in most substances and connects the refractive curve to the absorption properties, the absorption lines. This was a big discovery and a very difficult one. And it was early on suggested that the equations of the ether must be altered in some way in order to handle this kind of thing. And working with that conception, Helmholtz wrote the following. He said, well, let's just assume that the ether normally just transmits transverse waves. Think of it as an elastic solid, if you want, which is incompressible. Why incompressible? Because you don't want longitudinal waves in the ether, just transverse waves. Then he said, well, absorption is going on, so let's add an absorption term over here in the equation. And then he said, how am I going to account for anomalous dispersion? He says, suppose the following is the case. Let's treat matter, forget microphysics still, but let's treat matter as another continuous substance which is sitting there in the ether. I mean, you can't possibly envision such a thing. Two continuous substances. And let's assume that there is an interaction link between the two, so that if the matter gets displaced, again, a continuum by X amount, and the ether is displaced in the same place by Y amount, that a force is exerted on the ether equal to the difference in the displacements, and an equal and opposite force will be exerted on the matter in order to preserve action-reaction energy. Then you build two separate equations here. You build an equation here for matter itself. This has that dissipative term in it. And then you have the ether-matter link over here. And here you have the transverse wave equation for ether. You have a similar one for matter. And now you don't put dissipation in the ether, you put it in matter, and you put the ether-matter link here as equal and opposite to what it is down here. Run those equations through, and you have a complete explanation, quantitative, of anomalous dispersion. Works perfectly. So Drude and others beginning to think about this say, well, all right, okay, maybe we can get around our problems with this extra phase and so on if we start thinking about equations for matter which link up to equations for ether. And Lorentz, very famously, gets into the mix of this thing at this time. And Helmholtz is actually the first to suggest a modification of these mechanical equations